Hi, my name is Natalie Elliott, and this is my final project presentation for a social media sentiment analysis. Sentiment analysis is the process of examining and extracting emotion or opinion from text written by people. It usually captures sentiment on a positive-negative scale, but it can be used to analyze more specific types of emotions too. In this video, I provide the project's methodologies, key findings, results, and analysis. The problem I'm addressing in this project is to classify tweets as positive, negative, or neutral based on their expressed content using R programming language. To accomplish this, I used the supervised learning technique of decision trees and a sentiment classification analysis to sort terms into emotion categories based on sentiment scores. I also used text mining and visualizations to explore and further analyze the data. The dataset used was obtained from the Sentiment 140 dataset on Kaggle. It can be viewed at the URL on the slide. The dataset contains a whopping 1,600,000 tweets scraped from Twitter on April 6, 2009. After loading the data, the variables sentiment and text were subset into a new data frame for text mining and classification. The sentiment levels, according to the original dataset description, were 0 equals negative, 2 equals neutral, 4 equals positive. The text variables contained the content of the tweets. The dataset contained no missing values, and the distribution of sentiment values showed 800,000 as negative and 800,000 as positive, which suggested that there were no neutral values. This was at odds with the dataset description, but a search for neutral values confirmed this as true. A bar graph shows the distribution of tweets between the negative and positive values. It also shows how massive this dataset is, which is too taxing for R to process. So, a stratified random sample needed to be taken. Since classification methods are being used, the sentiments column must be converted to categories, also known as factors, so they can be processed properly. They were then given the preferred category labels of negative and positive. To take the needed stratified random sample, the data was shuffled and partitioned to 1/1000th of its original size. This gave a stratified random sample of 1,600 rows with 800 values for each negative and positive sentiments. The text variable values were then loaded as a corpus, which is a collection of text suitable for text mining tasks. The corpus, however, needed to be cleaned up. This process includes transformations to remove URLs and usernames, make everything lowercase, replace punctuation with whitespace. Otherwise, some words that should be separate are combined into one nonsense word. Remove special characters, remove numbers. Remove single letters, such as the use of the letter U for the word you. Remove stop words, which are common use words such as the, is, and, etc., that don't have substantial meaning or sentiment on their own. And stem the text. Stemming the text is when the root word is used rather than the word's different iterations. For example, reducing clicks, clicked, and clicking to click. After this, the text is left with extra space between words, so those were also removed. The next step was tokenization of the corpus. This is the process of breaking down sentences, or in this case tweets, into tokens, which are individual terms that are easier for natural language processing tasks to work with. To do this, a term document matrix is created. This is a table that counts the number of times a word occurs. This resulted in about 3,100 terms. The document matrix was then sorted by top frequently appearing terms and turned into a bar plot. The most frequently occurring words in the corpus are good, love, work, time, feel, miss, LOL, Twitter, night, and watch. A word cloud was created to display the words contained in the corpus. It shows the most frequent terms as larger and the less frequent terms as smaller. To figure out which words lead to positive or negative sentiments, I used a decision tree, which is similar to a flowchart. I removed sparsely used terms to ensure the decision tree has an easier time with classification. This reduced the number of terms to 213. A data frame was created to use the terms as column names, and the sentiments variable was added as the final column. This process retained the integrity of the original term locations and their corresponding sentiments. The data was then split into training and testing sets at a 70-30 ratio, respectively. This process retained the stratification of sentiment values, balanced with 560 for each negative and positive in the training data, and 240 for each in the testing data. The first decision tree was built using the training set without any control parameters. This allowed the algorithm to determine how large the tree should be. You can see a plotted version of the tree in the slide. It is small, with only 4 splits. The prediction abilities of the model were examined for the training set. This model's accuracy is 59%, which means it is predicting the 2 classes at an above average rate. Precision is 55%, which indicates that the model is about average at predicting the positive class and minimizing false positives, where something is predicted as positive when it is actually negative. Recall is 94%, which is very high, so the model is doing well with its true positive prediction rate and minimizing false negatives when something is predicted as negative when it is actually positive. The F1 score is a balance between precision and recall, and it's sitting at 70%, which is quite good. To optimize the model's performance, a second was built with cross-validation equal to 10. Cross-validation is useful for enhancing the performance of a model by having it train on several different subsets of the training data. The minimum value, or how many items need to be present for a split to occur, was set to 5. Complexity parameter, which represents the ideal place to stop splitting the tree, was set to 0. Unfortunately, there was no significant change to accuracy, precision, recall, and F1 score. These measures are identical to the previous model, which means that this model is likely as accurate as it's going to be. But the tree is much larger than before, so it needed to be pruned. The complexity parameter plot shows that the ideal place to prune lies between a tree size of 5 to 10, putting the complexity parameter value at around 0.0043. The tree was then pruned under this parameter. After pruning the tree, we want to see how this model performs with the test dataset. The pruned model shown in the slide has an accuracy of 56%, around 3% lower than how it was performing with the training data. The precision rate is 54%, which is a 1% difference from the training data. The recall rate at 93% had a 1% difference. The F1 score at 68% had a 2% difference. We can confidently say that the model's predictive rate with the test data is performing as well as it was with the training data, and that there is no indication of overfitting, which is when a model adheres too closely to the training data and then fails to accurately predict new data. However, 56% accuracy isn't ideal, and the underperformance of the model means that a decision tree may not be the best method of classification for this data. So I turned to another method of classification. The original sample of tweets was converted to obtain sentiment scores for words under the classifications anger, anticipation, disgust, fear, joy, sadness, surprise, trust, negative, and positive. It can give us a stronger understanding of the sentiments represented in our sample of tweets in greater depth than using only positive and negative. A bar graph of the 8 emotion categories, excluding positive and negative, was created to show that the highest proportion of emotions in the sample is anticipation, followed by trust, joy, sadness, surprise, fear, anger, and disgust, respectively. This indicates that the sample we have leans toward positive emotions. I then used an emotion comparison word cloud using the top 4 emotion classes to visualize which words are classified in each emotion category. This offers a better look into how words can be attached to certain sentiments. It's interesting that though anticipation and trust had the highest proportion of sentiments, they have the fewest number of words in the word cloud. This is likely because there were more of those words that indicate these emotions, but they occurred less frequently. The comparison cloud drops infrequently used terms, so this seems the likeliest case. Nevertheless, there are some interesting observations that we can glean here. The words father and brother are in the trust category, the word daughter is in the joy category, but the word mother is in the sadness category. It's also interesting to see Don, D-O-N, as one of the top frequent words under trust. It's unclear if this is a person's name, the word meaning to wear or put something on oneself, or something else. We can see the word nap in the joy category, which means naps bring joy to users. The words music and art are both in the sadness category, which means that users were tweeting these terms in contexts that convey sadness. We can also see the terms count and top in the trust category. It's not immediately clear why these were categorized this way without the greater context of the tweets. Some potentially troublesome categorizations include the terms black, lesbian, and fat, which are in the sadness category. Again, it's hard to tell without the greater context of the tweets whether these are the result of bias in the sentiment scoring algorithm. Regardless, there is an overall clearer indication of how these terms are used in relation to particular emotions. It's important to look at the positive-negative sentiment distribution too. The bar chart shows that positive sentiment accounts for just over 60% of tweets, and negative sentiment accounts for just under 40%. Most of these words fall into their expected categories, such as good, puppy, and vacation in the positive category, and hate, headache, and earthquake in the negative category. There are a few puzzling categorizations in the negative class, with mum, boy, words, and John seeming very out of place. There are also some strange categorizations in the positive category. Dawn has showed up again, along with title, cab, and top. Some concerning categorizations include black in the negative category and white in the positive category. Given how black was categorized in the previous comparison cloud, this may be indicative of bias present in the algorithm. Without context, some of these categorizations make little sense. Overall, though, we are seeing a much better snapshot of the general sentiments of these Twitter users than we were with the decision trees. It seems that, at least in April of 2009, the general sentiment of users were more positive than negative. However, it should be noted that neither the original dataset nor the sentiment scoring algorithm account for neutral sentiment. Tweets often contain neutral sentiment about mundane things like about to get ready for bed or similar statements. Neutral sentiment when performing a sentiment analysis on tweets needs to be taken into consideration. Furthermore, there is reason to suspect that there may be some bias present in the sentiment scoring process, which calls for further investigation. Ultimately, algorithms do what they're programmed to do, so if bias is present, It was programmed that way, but with effort, it can be removed or at least reduced to be scoring sentiment in an equitable manner. Thank you so much for listening to my project presentation. I hope you enjoyed seeing it as much as I enjoyed making it. Take care.